everyone. So today we are gonna look at how to solve a 5 times 5 system of linear equation, a 5 by 5 system of linear equation. So if you missed my previous class, you can watch this video. Okay, it's quite similar to the previous one, but in this video I am going to show you how to solve this big system. Okay, let me write it down. 2x1 plus x2 equals to 1. x1 plus 2x2 plus x3 equals to 1. x2 plus 2x3 plus x4 equals to 1. x3 plus 2x4 plus x5 equals to 1. And lastly, I have x4 plus 2x5 equals to 1. So if you look at this whole thing here, this is a big system. Okay, this is a big system. Usually you don't write the zeros there, but I just want to show you this is a 5 by 5 system of linear equation. Okay, again, you don't have to write the zero, but I just want to show you. So in a matrix notation, I can write this as 2 1 0 0 0 1 2 1 0 0 0 1 2 1 0 0 0 1 2 1, and I have one more. I have one more here, which is 0 0 0 1 2. Okay, this is a big matrix here, and these are my variable x1, x2, x3, x4, x5, and my b. These are my b's. 1 1 1 1 1 1 1 1 1. So what I have there, I have a big 5 by 5 system of linear equation. Okay, so I can write this in the form of ax equals to b. Okay, so I have, let me just change the color. I have ax equals to b. Okay, so you can solve this system of linear equation using any analytical approach. So you can use ERO, okay, to find the exact, right? To find the exact solution, I can use elementary row operation. I can use matrix inverse. Okay, how to find x, which is equals to take the inverse of a multiplied with b. Okay, these are some analytical approach that you can use to solve this system of linear equation. I can also use Gauss elimination approach. Okay, but what happened here, we want to solve this using a numerical method known as Jacobi method, Jacobi's method. Okay, this is our goal today. So I want to show you how to solve this system of linear equation using Jacobi method. Okay, let me just clear my screen for now. Okay, let me erase this one. We're not looking at homework yet. Okay, if you wanna write it down, you can, but we'll look at it next time. Okay, just erasing my screen so that we can look at how to solve that equation. Okay, so there you go. Okay, so Jacobi method works as follows. Okay, so what we do here, first step, or the step number 1 is to rearrange the equation, such as you will write in the form of x1 equals x2 equals x3 equals x4 equals x5 equals. Okay, that's the first step. So if you look at my system here, the one I wrote earlier on, we can see that to write x1 equals to, I have to look at this line equation here. So look at that equation. We have, let me just arrange this. Okay, I have x1 equals to 1 minus x2 divided by 2. Okay, so I have 1 minus x2 divided by 2. That's my x2, x1, and then for x2 I have 1 minus x1 minus x3 divided by 2. So I have 1 minus x1 minus x3 divided by 2. And then look at x3. To look at x3 here, this is my x3 here. So I have 1 minus x2 minus x4 divided by 2. So I have 1 minus x2 minus x4 divided by 2. And then we're going to look at x4. So x4, we'll write in terms of x4, right? So I have 1 minus x3 minus x5 divided by 2. 1 minus x3, 1 minus x3 minus x5 divided by 2. And lastly, last one obviously is 1 minus x4 divided by 2. So we have 1 minus x4 divided by 2. Okay, you don't have to look into that. Okay, that's the first step. Okay, you rearrange the equation in the form of x1, x2, x3, x4, x5. Okay, now to start this iteration, you need initial estimate. Okay, we can start with any initial estimate. So I want to start the initial estimate as this. Okay, so 0.6 for x1, 0.5 for x2, 0.5 for x3, 0.5 for x4, and 0.6 for x5. Okay, usually if the initial estimate is not given, you can use any initial estimate, doesn't matter. Okay, so based on this initial estimate, what I can say here now, let me just write it in this color. So this is my x1, this is my x2. I can say x1 not, x2 not, x3 0, x4 0, and x5 0. Okay, these are all my initial estimate. So now just start the first iteration. Okay, we're gonna start with the first iteration. I can also write the first iteration as I equals to 1. Okay, so to have first iteration, my x1 equals to, look at the thing here, I have 1 minus x2 divided by 2, but my x2 initial here is 0.5, so I will have 1 minus 0.5 divided by 2. Okay, so I have 1 minus 0.5 divided by 2. So 0.5 divided by 2 is 0.2500. Give your solution to 4 decimal places. Okay, places. Okay, now to find x2, we're going to substitute the other value initial here into the x2 equation. The x2 equation is given by 1 minus x1 minus x3. So 1 minus 0.6 minus 0.5 divided by 2. So I have 1 minus 0.6 minus 0.5 divided by 2. So that will be negative 0.4. 0.4 minus 0.5 is negative 0.1 divided by 2, negative 0.0500. Okay, 4 decimal places. And then to find x3, I think you got the pattern now. So to find x3, we need to look at 1 minus x2, which is 0.5, minus x4, which is 0.5. So 1 minus 0.5 minus 0.5 divided by 2. 1 minus 0.5 minus 0.5 divided by 2. Okay, so this is 0. Okay, you can press the pause button and take out your calculator if you don't have. Okay, you need to get calculator or any software that you can use to calculate this quickly. Okay, now x4 here, 1 minus x3, which is 0.5 minus 0.6. So we have 1 minus 0.5 minus 0.6 divided by 2. Okay, again we will have negative 0.05. Okay, last one, x5 equals to 1 minus x4. x4 is 0.5 divided by 2. So we have 1 minus 0.5 divided by 2. So 0.2500. So this is my first iteration. I'll write it as x1. I obtain as the first value is this one, second value is negative 0.0500, next value is 0.0000, the next value will be negative 0.0500, and then 0.2500. Okay, now let me just emphasize something. Okay, student can get confused. Okay, so to avoid the confusion, let me just tell you what's the difference between this one, okay, the superscript and subscript and superscript here. Okay, they are not the same, okay. This refer to x1, the variable x1. Okay, this refer to the iteration, okay, the first iteration that I have done. Okay, so they are not the same, and don't get confused. Okay, if you have a second iteration, then you will have x, the second iteration. Okay, and in the second iteration you can have all the solution for your x variable. Okay, so please take note. I don't want you to get confused. Okay, now continue what happened here. So we can stop, but our solution will not be accurate. Okay, but this is just first step. Okay, and we should continue with the second iteration. Second iteration, which is to find x2. So to find x2, you will go through the same process that you do the first iteration, but now you have a different value. This is my updated value for x1, x2, x3, x4, x5. Okay, for x2 for the first iteration. These are all my updated value. So I'm going to use that value to find my new x1. Okay, I hope you're with me. So continuing the process, we have, usually at this stage I will ask the student to just do on your own, because once you know the concept, you just have to keep doing it, right? Okay, so x1 will be 1 minus x2, which is this one, 0.0500 divided by 2. Okay, so we have 1 plus, is it 1 plus 0.05? So divided by 2 is 0.5250. And then the second equation is 1 minus x1 minus x3. So we have 1 minus x1 minus x3, 0. Okay, divide by 2. And use your calculator, you should get 3750. And then the next iteration, x3, is given as 1 minus x2 minus x4. Okay, too many minus here, so just be careful. Divide by 2. So we have 1 plus 0.05 plus 0.05 divided by 2. So we have 0.5500. And then x4 equals to 1 minus x3, 1 minus 0, minus x5. x5 is, what do you get for x5? 0.25. Okay, so what we have, divided by 2, 0.3750. Okay, and then what we have, the next one is my x5. x5 equals to 1 minus x4. Okay, what is my x4? Negative 0.05 divided by 2. That will give me 0.5250. Okay, so you have obtained the second iteration values. x2 consists of x1, which is 0.5250, and then you have x1, and then x2 0.3750, x3 which is 0.5500, and then you have obtained x4 which is 0.3750, and my last value which is my 0.5250. Okay, these are all the second iteration value. Now you need to keep doing. Okay, you need to keep working. Continue your iterations until you obtain similar result with your previous iterations. What that means? What that means? It means that, let's say this, my second iteration is like this. Now I'm doing my third iteration, and when I do my third iteration, I've obtained a similar result with my second iteration. Okay, you can move furthermore. You can try to do your fourth iteration, and even when you do the fourth iteration, your solution is similar with my third iteration and my second iteration. This means your solution has converged to the exact solution. So stop your iteration. Stop your iterations once your solution has converged. Now, what does converge here means? Converge here means approaching your solution, approaching to the exact solution. That's what converge here means. Okay, so this is when you stop your iteration. Okay, so this is so we want to know actually. So my question to you is, what is the exact solution? Okay, what is the exact solution? So there are two ways to find it. The first thing I want to show you is using Scilab. Okay. Okay, so what I want to do today or right now is to use Scilab and solve using Jacobi method. Okay, so before that, let's check what is the exact solution. Okay, let's put the matrix A equals to 2, 1, 0, 0, 0, 1, 2, 1, 0, 0, 0, 1, 2, 1, 0, 0, 0, 1, 2, 1, and then I have 0, 0, 0, 1, 2. Okay, so this is my matrix A. Matrix B is given as 1, 1, 1, 1, 1. I hope I have 5. So to find the inverse, okay, which is to forget x, I have inverse A multiplied by B. Okay, so this is my exact solution. Now this window, console window in Scilab, works as a calculator. Okay, so you can find a simple operation like find the matrix inverse, arithmetic operation like multiplication and so on. But if you want to write a code, you cannot use console. I'm not recommending you do that. So to write the code for Jacobi method, so go to this application and open SciNotes. Okay, so a white screen will appear. So this is SciNote. Okay, so the SciNote will look like just a complete white screen here. So now you can start coding. Okay, so I can use this dash dash as a command. So what I want to write here, solving system of linear equation using Jacobi's method. Okay, and in each line you want to type, you have to use this comment symbol. Okay, so what is the date today? 23rd, 10, 2020. Okay, so this is how you start coding now. So if I look at my Jacobi method that I did earlier on by hand calculation, I need to have initial estimate. So what is initial estimates? So I have my x1 equals to 0.6, x2 equals to 0.5, x3 equals to 0.4, x4 equals to 0. I'm pretty sure x3 was 0.5, x4 was 0.5, and x5 equals to 0.6. Okay, these are the initial estimate, and then I need to have my equation, the 5 by 5 system of equation. So write your equations here. So what is the equation you wrote? So you don't have to comment everything. So for your case, I'm just going to do that. Okay, what's the equation that we wrote? We have x1 equals to 1 minus x2 divided by 2. Okay, then x2 equals to 1 minus x1 minus x3 divided by 2. And then I have x3 equals to 1 minus x2 minus x4 divided by 2. And then I have x4 equals to 1 minus x3 minus x5 divided by 2. And x5 equals to 1 minus x4 divided by 2. Okay, this is the 5 by 5 equation earlier on. Now we have defined x1, x2, x3, x4, x5, and we have also used it here. But now how to make it, like how to say that you want to do it for many iterations, like 1 iteration, 2 iteration, 3 iteration. So I need to use a loop for I equals to 1 to n. Okay, I'm going to take out this n here, put it all the way in the bottom. Okay, so this here means I am going to, every time Scilab read line by line, first line, this, we'll go through this loop, and this, anything in this loop here will run for many iterations. So what this thing means, I equals to 1 to n mean. Okay, let me just show you in Scilab. So let me just clear the screen, CLC to clear the screen. So I equals to 1 to 10. Let's say n is 10. Meaning it gives me a number from 1, 2, 3, 4, 5, and so on up to 10. Okay, so now we have 1 to n. So let's write n equals to 20 to start with. Okay, now for 20 iteration, the computer will read line by line. Okay, first this is a command. It will read this one, nothing. It's just a command. And then it will remember, oh, x1 equals to 0.6, x2 equals to 0.5, x3 is 0.5, x4 is 0.5. Okay, so when come to x1, so it will use whatever memory store for x2. So if we recall, in line 7, it read x2 equals to 0.5. So it's going to put the value of x2 here, divide by 2, and then you obtain x1. And then when you read the line 15, where x2 equals to 1 minus x1, x1 here is going to use the updated value of x1, which you obtain here. This is not how Jacobi works. For Jacobi, you use all the initial estimate to start with. So you need to change the variable name to x2 new, x3 new, x4 new, and x5 new. Okay, now this is good. Okay, so read all this, save it in the memory, and then when come to x1 new, it will use this x2 that is stored above here as an initial estimate, and so does x1 and x3 here as an initial estimate. Put it in, and then now you have to update your x1. x1 will be equals to x1 new, so that the second iteration, it uses the updated value of x1, x2, and x3. Okay, I hope you're with me so far. So x5 equal to x5 new. Okay, let's go through this. Let's go through this one more time. So it will read line by line up to line 6. It will say, it will remember x1 equals to 0.6, x2 0.5, x3 0.5, x4 0.5, x5 0.6, and n equals to 20. And then it will read line number 12, which is just a comment. In line 13, it will go to the first iteration. For I equals to 1, it will compute my x1 new, x2 new, x3 new, x4 new, x5 new, using all the values from the initial estimate. And then it will say, my new value for x1 is x1 new, which is this one. And my x2 new is my next x2. And x3 will be my x3 new, and so on. And then end the loop, go back again to the loop for second iteration, third iteration, and so on. So this is how Jacobi works. So you can try to save it, give a name for your coding. So I usually store it on my document. So just say Jacobi. I already have it. I'm going to just replace my code.
Okay, so this is now works fine, but now you have to print out the solution. Okay, so how I want to print out the solution, let me show you on my whiteboard.
Okay, so what I want to do here, I want to produce in Scilab this result. I, x1, x2, x3, x4, x5. So I is 1, I is 2. So the first iteration I have shown you, what did you get? You get this answer, 0.25, negative 0.05, 0, negative 0.05, 0.25. So let me just write here. So I have 0.25, 0, 0, negative 0.05, 0, 0, 0.0000, negative 0.0500, and then 0.2500. And then the second iteration, I have obtained 0.5250, 0.3750, 0.5500, 0.3750, and 0.5250. Okay, and we stopped at the second iteration. We didn't find x for the third iteration, right? But we will let Scilab to use it. So let's separate it with a line. So I want to produce this table on Scilab. That's my next step. Okay, I'm not getting the box right. Okay, so this is what we want to find. We're going to produce this. So not just 3, up to 20 or 30 or any number I can. Okay, so let's see that. So how we can create a table in this form that display all the result for I values of iteration, all the x1, x2, x3, x4, x5 value.
Okay, so we want to print out the table exactly like what I've shown you in whiteboard. So go back here and you need to use mprintf quotation mark. So every character that I've shown you, you have I, you have x1, you have x2, x3, x4, and x5. Okay, and every here you want to print out the variable, the character. So you use %s in Scilab, refer to as a character for %s, and then we have for everything that we have defined here. So I need to have, let me just arrange it. So 1, 2, 3, 4, 5, 6, because I have 1, 2, 3, 4, 5, 6. Okay, so %s here refer to character that you want to print it out. Okay, and then I want to put a line, right? So I have a line, so mprintf. So just do the dash dash dash. You can do long, but you can correct it later on. Okay, that's it. And then that will, let me just show you what it will give me on the screen. Okay, go back to my screen. Let me just clear the screen so that you can see it. CLC is to clear the screen. Okay, execute again. So this is what I get. I, x1, x2, x3, and the I is not what I want. So you need to have a new line here, /n for new line, and then this one also /n. So let's check. Okay, there you go. Okay, now I want to have a space between I, x1, x2. So to have a space, you just put a number in front. So let's start with 8, 8, 8, 8, 8. So 8 here refers to like 8 space. Like if you're using your Microsoft Word, you always press space bar 8 times. Imagine. That's what it means. So if I run it one more time, I will get, yeah, there you go. I have a space now. Now you can also extend the line. So extend the line. Okay, so that's it. So let me just what you want to do next is to display the value. So print screen here, put it down here. Okay, but now I'm not printing character, I'm printing the variable I, the values of I, x2, x3, x4. So you don't need quotation if you are displaying the value x4 and x5. Okay, it's not character. I here, this I here refer to integer, so %I. My x1 is in floating point, so I have, instead of s, I'm going to use f. F for floating point. Okay, decimal places. And then I have 4 decimal places, so dot 4. Dot 4 here refer to 4 decimal places. Okay, now let's run it. Okay, let's run it and see what I get. There you go, look at that. Okay, so this is all my result. I need to extend my line and give more space, I guess, for the values. So just extend the line, just add more line here. And then you can put more space if you want. Okay, and maybe let's check again. Let's check again what I have. Okay, looks good to me, but just x1 need to in the middle and so on. So let's clear the screen and shorten the distance. So I'll put 6 here. 6, 6, 6, 6, 6 instead of 8. 8 is too widely spaced. Okay, there you go. Okay, now x2, x3 is not even, so I guess I'll just stick with 8 here for these 3 values, so that what I have now. Okay, pretty good. Unless you want to move on your x, you can just adjust it by pushing, give more space. Okay, so I can put it 8 here and so on. This is my result, which okay, so I can adjust it more, I guess. So what I want to do here, okay, adjust x2, make it in the middle. Okay, so this is my x1, x2, make it 8. Okay, let's see. Execute the button. There you go. Okay, this is perfect. So we have exactly like what we have written on the Microsoft whiteboard just now. Okay, x1 value, x2 value, and so on. So we have obtained up to here, and you can see that it's exactly the same like what I've written. Now, what can be summarized from this table that you have displayed? We can see that up to 20 iteration, the solution still haven't give me similar to the exact, right? So I can increase the number of iteration. I want to put 100 now and execute the button to see what you get. Okay, there you go. You can see that at starting 66 iteration, the solution is producing all the same answer, right? So we can say that the solution has converged to the exact solution at the 66 iteration. This is what converge means. Approaching exact, and the rest computation give you the same answer. Did you see that? So it's all the same. Okay, so I can also say that in order for that Jacobi to solve that 5 by 5 system of linear equation, it needs 66 iteration. And if you're using your handwriting calculation, you will take forever to come to this 66 iteration. That's why programming is very important when you are solving using numerical method. Okay, so usually you'll put high value of n, and now I know I just need 66 iteration. And the other thing is the initial estimate. Okay, I can actually use different initial estimate. Let's see if I use 0, 0, 0. Now what do I get? Press the execute button. Okay, so I can see that if I use all 0, my solution has converged at the 67 iteration. Okay, the only difference is this is exactly the same like the our exact solution, right? There's no negative sign here, so I don't know why the negative signs appear. But if you use a different initial estimate, you will still get converge to the exact, but with different number of iterations. Earlier on, I said 66, but this one needs 67. Okay, can you get anything closer? Let me just do like that, 0.2. Because I know the exact solution, so I'm just going to cheat a bit. So x1 0.2, x2 0, x3 0.2, x4 0, x5 0.2. Let's press the button. Okay, for 100 iteration, let's see at what iteration it converges. 59 iteration. So I can see that at 59 iteration, the solution has, oh no, actually not 59 because I have this value here. 62, no. 63 iteration. The solution converges at 63 iteration, which is shorter than 67 and 66. So initial estimate plays an important role. Okay, important role to get the convergence. So if I change everything, maybe this one to 0.5, this one to 0.5, let's see, let's try one last. And what you get? The solution converge at 66 iteration. Okay, so the summary that I can say, to solve this system of 5 by 5 linear equation by using Jacobi method, you need to do at least more than 66 iteration. Depends on your initial estimate that you choose, but the solution will converge, will approach the exact solution. It's just depending on how many iterations that you need to do. Okay, that's all for today's class. I hope you can try again using Scilab, used for different types of problem. And we'll see you in the next class. So that's all. Thank you.